started out by looking at software productivity concerns from a high up level bird's eye view, and slowly as the day progressed, we plunged into some of the issues, looked at them deeper, with Alicia taking you down to hands-on level. Now I'm slowly bringing you back up to the bird's eye view again, at least partially, in these two presentations that I'm going to be covering. So you saw a slightly different colored version of this picture first thing in the morning today, which is what goes on in this life cycle of a scientific software. And so this one is from the perspective of a multi-physics, multi-component simulation scientific software, and that the detailed steps are involved with that, but you can take it as a general representation of the kind of schematics that you would come up with for most of software that relates to scientific endeavor, scientific discovery through computation. Again, this one is specific to the kind of modeling that you would do with partial differential equations, but that does not lose the generality of this kind of schematic and workflow for development of scientific software. It applies to other things as well. The specifics may be different, but the overview is the same. So what happens in a typical scientific workflow? You have a phenomena in the physical world that you are interested in understanding more. So the first thing that you do with that phenomena is you formulate a mathematical model for it, which will be some form of equations. They can be partial differential equations for vast majority of them, or they can be other kinds of equations, algebraic equations, and so on and so forth for some of the other domains. Notice that along with the arrows, I've also labeled the activity that is going on in going from one step to the next, and also the kind of expertise that is needed in that particular part of this workflow. So when you're transforming a phenomena in the physical world to a mathematical model, what you need is somebody who is a domain expert who understands the characteristics of that physical phenomena and can express them or can approximate, because at best what you can do is approximation, not really exact representation of that phenomena. So that person, this domain expert, is able to approximate that phenomena into some form of equations. Now good, you have these equations. In the very early days of science, it was possible to get an analytical solution to the equations that people were interested in, and so you would just do a paper and pencil and get a paper and use paper and pencil and get results for the equation, and you're done. Those days are long gone, right? Because now you're looking at things that do not have easy analytical solutions, plus anything of interest is typically has nonlinearity into it. So what you do then is you discretize your equations and convert them into a difference equation. Discretizations come in many forms. You can have a discretization that is based upon finite differencing, finite volume, finite element, other methods such as spectral methods, and so on. Each of these discretizations have their own characteristics and their own numerical methods that apply to them. So once you have your difference equations created, then you start to look for the kind of numerical solvers that are going to be able to solve your equations. And so the expertise that comes into play here is an applied mathematician who develops these numerical algorithms. And then you go ahead and you implement the numerical algorithms, and after implementation you do a validation, which in this set, I'm applying the term validation very narrowly here in this context. Validation is against the observations related to the very same phenomena, which means that in this particular validation, what you're doing is you're making sure that you are modeling what you think you're modeling. This is a completely different question from other kinds of validations, such as validating your data, validating your algorithm, and so on. This is just verifying that you have the phenomena that you are trying to model is the phenomena you are modeling. But notice that there are not just these bold arrows. that are going around here. There are also the arrows that are sort of feeding back, and that is because of the nature of the scientific computation. It is that, as Catherine had said in the morning, that vast majority of these steps are themselves under research. So sometimes you may have to go back to one of the earlier stages because of insights you gained and your model become a higher fidelity model. Sometimes you may have to go back into an earlier stage within this workflow because someone externally to your project found a better algorithm or a better model that applies better to a phenomena, and you may want to replace it. So again, and sometimes what can happen is you have an equation and you apply a numerical solver and you find that it doesn't converge or it doesn't give the kind of answers that you're looking for. So you have to go back and see if sometimes you may end up having to change the equation depending on the kinds of solvers that are available. This happened once to a group that I was working with, is that I'll be talking later about this code, the Flash code, where the radiation that they wanted to model was done with flux limited diffusion, and then they applied a simple ILU solver from one library in there, and it turned out that the results that they got were completely useless because they were not able to resolve the features that needed to be observed. And so in the end, it turned out that the algorithm that was more applicable to that was an algebraic multigrid algorithm. But in order to implement that algebraic multigrid algorithm, there needed to be an interface with a library, and therefore the discretization had to change in order to get the right answers. So sometimes those kinds of feedback loops that need to happen. If a new numerical method is getting implemented, then it is not merely enough to verify that you are getting expected answers. You also have to do things like convergence testing on it and the stability of the method. You have to know the regime in which that method works, the range of validity before you apply the method to it. And then when you're doing the implementation, the expertise that comes into play is software engineer. And for the validation, again, you need a domain expertise for looking at the observations and certifying that the results are valid. Things don't stop here. Because then if you're running the code on a large scale machine, then as Catherine mentioned in the morning, performance becomes important because you need these resources are rare and valuable resources. You do not want to be wasting them. So the performance of the code becomes important. And that can lead to changes in implementation in a feedback loop right around there. And you need more kinds of expertise that come into play. For example, you may need optimization experts. So what this slide is effectively telling you is that there are many moving parts and many degrees of freedom that are involved in this process of making scientific discovery through computation. All of these moving parts have to come together. They have to play well. There has to be an interoperability, not just among various components in the code, but also in the expertise that you bring to bear on this kind of problem solving. With this in mind, there is one more view that you can have of a life cycle. Here I have collapsed many of the details from the previous schematic, because what I want to emphasize is that there is another aspect to doing a software development, scientific software development. So you can have a mathematical model, for example, that has two kinds of physics. Each one may be modeled using a different discretization and may be solved using a different different numerical algorithm. So the first one that we have here is that you have your approximations, numerical algorithms. You check for its correctness, stability, and convergence, and you're good to go. Now you add another method to your code. But this time, this particular phenomena, supposing there is something that is available in a numerical library. So now you need to bring in the link to a numerical library, and then you have that loop again, which is where you're using the arrow is wrong. The arrow needs to be in the other direction there. So you have a numerical algorithm that you bring in from the numerical library, and here the validation is used in a different sense. Here you're validating that the algorithm that you're fetching in from the numerical library is working in the way that you expect it to work. So you can be developing two components within the same code in two completely different ways. One is when you're doing the implementation yourself, and another one is where you're bringing in a numerical library. Then when you have these kinds of multi-physics codes where there are components that need to interoperate with each other, there is one thing that you cannot do without, and this thing is a framework or a backbone of some sort that enables these various components to be composable in order to generate an application. And so this is what we call the infrastructural framework. And infrastructural framework has its own life cycle. The capabilities, which are then the physics solvers, have their own life cycle, and then they interoperate with one another, or rather couple with one another at different points. So when you're looking at how the life cycle of a framework design follows, you do a requirements gathering in the sense that you try to find out what kind of discretizations you're going to be working with, what kind of solvers you're going to have, what capabilities you want, what degree of extensibility you want, and based upon that you converge on a framework design that is going to be that will work well for you. You design the framework, you implement it, you test it, you maintain it, and occasionally if you are adding newer capabilities to the code, it may come to pass that you may need to augment the features that you already have in your framework, in which case you go back to the design of the framework and the requirements. And again, later on I will give you an example of where this needed to be done in Flash, which is the code that I'm most familiar with. Where the physics model then has to know about the framework is in the places where, for example, a good framework will have APIs for all of its components, and it will constrain the way in which these components work with each other, and therefore the API design has to conform with the dictates of the framework. And the second place where the physics capabilities have to directly interact with the framework is for testing, and for they dictate what augmentations may be needed into the framework. So and the kinds of capabilities that you may have in the framework is your discretizations, your so if you're working with mesh-based solvers, it's the mesh, it's the I/O, it's the runtime parameters, if it's any kind of logging facilities that you might want in your code, I already mentioned runtime parameters, and generally things that are not specific to a particular type of physics or a particular type of solver, but are general purpose services that are applicable across the board. So with this in mind, we can think about how do you architect a code, because the code architecture is essentially what is your framework. And some of it, of course, leaches into the physics capabilities also, but by and large, it is the framework where you figure out the software architecture. So the first thing that you need to do in designing a software architecture is you have to take a stock of what your requirements are, because I will concede this upfront, that having an architecture, designing an architecture for a software is an overhead, because it is a given that if you could magically generate a completely flat spaghetti code in assembly of the target architecture, there is nothing that is going to run faster than that, right? But that's not an option. So we accept certain kinds of overheads in order to have greater productivity, and in that sense, architecting a code is an overhead, and you have to see where you have to, and the motivation for investing in the architecture is to reduce your technical debt for future extensibility in the code. But before you do that, you have to understand what kind of technical debt you will be acquiring depending upon what is the scope of the code that you're developing. And so it's very useful to understand the trade-offs that you're working with. So your target software could be just a proof of concept, in which case, if you're not the obsessive kind of person, and if you're 110% sure that software is not going to live on to become some sort of regular tool for people, then you don't have to worry about architecture at all. If it is, and some of these applies to verification and so on, but as soon as you get into the mode where your software is for exploration for some phenomena and everything below that, such as experimental design, product design, et cetera, you are already in the area where you have to pay attention to software architecture, because you can take it from me that no software is static in the scientific world, in the sense that you can never say that I'm done with my software, that I don't need to make any changes. The software project that I've been associated with, Flash, has been in existence for nearly 20 years. Till today, I have not heard of a single production schedule that has been run with that software where people did not need to do some customization or the other for doing their work. And when I'm talking about customization, I'm not saying that they're just changing the parameters that they're feeding into it. No, they're actually having to change some code somewhere in order to meet their requirements. So your target that you have with your software should dictate the rigor of the design and software process while being cognizant of the resource constraints. So, well, I've already said this bit. So, what are the desirable characteristics of software architecture? It is that you want extensibility, because all of the users are going to want to modify, customize, extend capability in some way or another. You want portability, because typically a software of this kind lives way longer than a platform lasts, and so the architecture changes from under you. And now that we are in this times when even the same generation platforms are so different that if you make your software work on one class of platforms, it will not work on all of the other platforms. So portability is very important. Performance and performance portability are also equally important, because like I said, the machines are rare resources. If you want to use them well, you have to be prepared to invest in performance portability. And the last point, maintainability and verifiability, goes back to the reproducibility concept that Mike talked about earlier, because you want to have believable results. You want people to believe in what you're producing, and you want yourself to be confident that the results that you're producing have some value, are scientifically valid. So in order to put these features into your software, there are certain implications in what you need to do. So in order to have extensibility and maintainability, you need to have well-defined structures and modules, which means that modules are encapsulated. You want to make sure, insofar as possible, that the modules communicate with each other only through their defined API, and that there are no lateral interactions among modules. Also, you have to understand who owns what data, because a lot of errors that happen in scientific simulations come about because the data ownership is not properly understood. And even if you have a modular code, if you don't have an arbitration on who has the read and the write access to a particular data item, it can lead to inadvertent changes during runtime that may lead to wrong results. Then, in order to get performance, given the memory hierarchy that we have in the platforms, you have to increase the temporal and spatial locality of data. So earlier in the program, you would have been exposed to what happens with memory management, cache hierarchy, and the performance hit of the performance degradation due to cache misses. That is what comes into play here when you're talking about spatial and temporal locality. So spatial locality is when you fetch a cache line into your cache, it doesn't just bring in one data item, it brings in a whole cache line. And if you're able to use the data that is fetched in along with it before you throw it out, then you have better use of your cache. Similarly, if you're able to reuse the data that you fetched into the cache over and over again, you have better performance than if you're throwing data out every time back and forth. In the current environment, in the current computing environment, it used to be that the floating point operations were considered to be the most expensive part of a calculation. So the emphasis used to be on minimizing floating point operations. But in the way things have changed in the last few years, the floating point operations are nearly free. The real cost of computation exists in data movement. So you want to minimize data movement and you want to maximize scalability because you want to be able to use large platforms. And then for verifiability, you want the output, you want to be able to put out data for critical components, and you want to be able to test at different granularities, as was explained by Alicia in the lecture on testing. The thing though with the scientific codes is that there is a thing called reality. And this thing called reality is that reality, the physical world, is messy. If it wants a lateral if it wants a tight coupling between the two different models that you need to model the phenomena, those lateral interactions have to happen. Otherwise, you're not going to get the right answer. And so similarly, there are bells and whistles that exist in all of these algorithms. And here I have a favorite story about one particular time we needed to do a simulation. And we were told that our hydrodynamic solver was 5 times slower than the hydrodynamic solver that this other group had. So we said, okay, we should use their hydrodynamic solver. Our code being extensible and composable and so on and so forth, we brought it in, we ran. The simplest test we ran, and in the domain we had striations where it was supposed to have been smooth. So we said, why is this happening? Well, this was the one they were using for the purposes of benchmarking. So even though it correctly implemented the algorithm as it was published in the paper, it had bypassed many of the bells and whistles which would make sure that if certain things were happening, that they were handled appropriately, and they were removed because they're exactly the kinds of things that lead to edge cases, corner cases, and branches. And so their performance was better, and because no one was interested in the results, it didn't matter to them, right? So we said, okay, this is not working fine. We need something that has these bells and whistles. So they gave us the next version that they were using in some of their simpler smooth flow problems. We had shocks. Again, the answer was that things got a little bit better, but not completely better. The interesting thing is, finally, the version that we got from them that gave the answers that were comparable to our version of the code were within 10% in performance. So those bells and whistles, they are necessary for the accuracy of your solution, not and they get in the way of doing a well-modulated structured code, and they get in the way of designing your code. So, and the other things that happen is that the same data layout is not necessarily good for all solvers, so you may need transpositions and so on. So all of these are changes that, and then there are things that get in the way of locality and scalability also, because if you need a solver that has low arithmetic intensity, did you get introduced to the concept of arithmetic intensity earlier in the course? Okay, so you know what low arithmetic intensity is. It is that you fetch a data and you don't do very many operations on it before you have to throw it out. So if there are solvers with low arithmetic intensity but have these hard sequential dependencies, there is no getting around them. You just have to do them. And the other thing that happens is, for example, if you have adaptive mesh refinement, and I'm sure you've been introduced to adaptive mesh refinement earlier in the week also, is that the proximity, because you want to fill the halo of guard cells around your in a box that you want to operate on, so you want proximity between neighboring blocks, but that is at cross purposes with the ability to distribute work evenly. And so you have to, again, you have to think about the trade-off of where you want, what do you want more, what helps you more, proximity or equal load distribution. So the question comes, how do you tame this complexity? Because it is a very complex process. There's nothing easy or simple about it. So in order to tame the complexity, the first thing that you do is you differentiate between the types of functionalities in the code. And a little bit of it talked about is this breaking up of your code design into a separate part, which is framework and the physics capabilities. And the reason for doing this is that frameworks are relatively stable. So the model and the numerics are more likely to be a subject of research on a continuous basis, but the framework doesn't need to be. So you should handle, and the I/O, et cetera, and the meshing, et cetera, are all relatively stable. So you want to keep them, you want to develop them separately, and so you hide the complexity of the framework, the mesh, the I/O, et cetera, from the physics insofar as possible. And this is what goes back to separation of concerns, the concept that Catherine introduced earlier in the day today. Did anyone before Catherine talk about separation of concerns to you in the course? Okay. Well, since I did not get a very enthusiastic response here, I assume that being told about what separation of concerns is still okay. Here, separation of concerns is that because these projects require different expertise coming in and different concerns of having to deal with the numerical, so the model complexity, the numerical complexity, the parallel complexity, the data locality complexity, the synchronization complexity. Insofar as possible, you want to design your framework in such a way that these complexities are handled in different sections of the code in some sense, and so that people who have the right expertise can focus on what they are doing and not have to worry about knowing the details of all of the other aspects of the code. And so what you do is you identify logically separable functional units of computation, infrastructure from solvers, from monitors. Monitors are what are logging the progress of your simulation. And then you encode this logical separation into a framework where the infrastructure units form the backbone and handle all of the global scope data if your applications allow that, if your application allows that. Because if you are able to hide the scope of global data from the rest of the applications, it becomes much more easy to make it extensible and plug and play. So what you want to do is you want most of the data to be owned by infrastructure, only small amounts of scalar data that does not percolate across units to be owned by individual units, and that is a necessary condition, not a sufficient condition, but a necessary condition for a sort of plug and play model that allows for extensibility in the framework. And then you absolutely have to separate what is exposed from what is private to the module, and then you define interfaces. So now I'll go into an example from Flash, like I said, the code that I'm most familiar with, which does exactly this. It takes different kinds of units and separates them and treats them differently from one another. So even the architecture of the unit actually can differ from the type of unit that you are working with and the way they're handled when you're composing together a code. So Flash has 5 types of units. There's the infrastructure units, grid, I/O, et cetera, et cetera. Grid owns the discretized mesh and all the state variables. All of the state variables that you are going to carry around in your simulation, grid owns them. I/O and grid are very much more tightly coupled than any other unit. So in Flash, there is a clear delineation between there is a clear, so each unit owns the data it owns, and the other units can access it only through accessor functions and not directly. The exception being grid and I/O, because of performance reason, I/O has complete access to all grid data. So here is the thing about being judicious and not letting your religion get in the way of a good design, right? Infrastructure also manages all of the decomposition and scaling. Then there are physics units. So there is the hydrodynamics. Most of the applications in code are compressible hydrodynamics or magnetohydrodynamics. And gravity and radiation and resistivity, material properties, source terms, et cetera, et cetera. There's a lot of capabilities involved in it. It's a community code for 6+ communities, very diverse 6+ communities. These units require grid to operate on, and they do not, so when they operate on a grid, they've been designed in such a way that they cannot differentiate between a block with its surrounding halo versus the entire domain. So as far as they're concerned, what they're seeing is the entire domain that they're operating on. Then there are monitoring units, which are log file timers that they just log the progress and the timing information from the run. There is these two units, the driver unit and the simulation units, are again completely different from all the other units we've seen so far. The driver unit implements the time stepping, but in addition to implementing the time stepping, it also orchestrates the entire application by determining and dictating the operations that happen, interoperability among various units that are coming into play. Simulation unit is where you start an application. So Flash is not a code which you build once like a library and then run it over and over again. No, Flash has many capabilities that a typical application will not even see. So the way it works is that each of the units have some meta information about the dependencies, like the units that it needs, the units that it won't work, the state variables it needs, the runtime parameters it needs, the region of validity of runtime parameters and the region of validity of the solvers and so on. And there is a configuration script written in Python which parses this meta information and puts together a self-consistent application that then you can build and run. And chances are that any given application will use no more than 30% of the code base. Okay, so the simulation unit is where you define the application. So when the setup script starts to parse, it starts to parse the meta information from the simulation unit. This is where you define your initial conditions, your basically any characteristics of the application that you're trying to run, and also you specify the physics units that you want to use in your simulation. Another thing that is unique is in simulation unit is that this allows you to include customization of anything, any part of the Flash source code existing anywhere in the source tree, however small a function. If you place an implementation of that in your simulation unit, it overrides the existing source everywhere else in the code. So you can very selectively customize the parts of the source that you need. And this has been extremely useful for moving from one domain to another. So here is an example of a unit. This is the most complex unit in Flash. This is the grid unit. The blue is, so the API exists at this level. A unit can have subunits because each subunit then encapsulates a particular type of functionality. For example, grid particles encapsulate all of the functionality that is needed to, so Flash's grid is Eulerian, but it needs, in some simulations, Lagrangian characteristics are followed, and Lagrangian framework is used for many other purposes as well. So grid particles handles everything to do with the Lagrangian formulation within the code. Grid main owns the main mesh. Solvers is where generic solvers like the multigrid, the FFT, et cetera, sit that can then be called by different physics for use, and then BC is where the boundary conditions are implemented. So whatever is at this level is inherited at everything below, but anything at this level cannot be seen at the above level. And that's how we ensure the sort of sanity in the code base. And then here is an example of the kind of challenges that you can have in a unit design. The most difficult to design unit, without exception, in Flash has been the equation of state. And the reason why equation of state is a difficult thing to define is that it's a 0D solve, which means that it's a strictly pointwise solve. You don't have to do any stencil update, and there are no dependencies on the side calculations at all. But there are at least, I want to say, 6 different flavors of equation of state supported by Flash. They range from simple ideal gas gamma law to ionized plasma to table lookups and so on and so forth. And sometimes you do a table lookup and then you do an iteration upon it in order to complete the calculation. So there are several reusable calculations, and vectorizing them is useful for performance. But then the other physics units demand a great deal of flexibility from it, because sometimes they just want to apply it on one, sometimes they just want a scalar value and they want to compute, if they have pressure and energy, they just want, density and pressure, they want the energy, and so on and so forth. At other times, they want them on a subset of domain. Sometimes they want it on a large section of the domain. Sometimes when you're operating in the adaptive mesh mode, then after you've done the ghost cell fill, you want to run the equation of state in order to make sure that, because there is interpolation going on, that your all of the cells are at thermodynamically consistent. So you need to run the equation of state on those ghost cells only. So what ends up happening is that you have to have interfaces that allow for all of this flexibility. And then there is another complication, is that overall energy and internal energy, sometimes their difference in their accuracy level is enough that the internal energy can lost in the machine precision. But it is important to get the right answer using that in some circumstances, so you need to still keep that around. And all of these things make it very difficult to design a simple interface that would allow EOS to be used in every way that the users want to use it. So what do we have? We have a hierarchy in complexity of interfaces. We absolutely have pointwise equation of state solver for every incarnation of equation of state that we have. So we have a scalar input and output for single point calculation. We also have sections for blocked input and output, and what we do is we provide wrappers that consolidate individual points into vectors before feeding it to the equation of state unit. And then, so what this does is it does different degrees of control to different users, and then in addition to that, the interface has mask. And what mask allows you to do is, because some of the callers will also want derivative quantities that are computed inside equation of state, but if those derivative quantities are not wanted, then those equation of state calculations are going to be redundant calculations, so you want them not to be there. So you have mask, which can inform the equation of state module that these particular quantities need to be computed or not. So in the end, so it's a very elaborate machinery of masks and defined constants, but eventually we have boiled it down to some 3 or 4 interfaces that work together. So this is how it can be challenging to design an application. But now we have all completely new challenges facing us in architecting applications. So in the last 2 decades, the machine models were sort of stable and uniform. We had a distributed memory model. If you programmed for one RISC machine, which means that you optimized the spatial and temporal locality of your data fetching and you minimized the communication between nodes, you were guaranteed to work reasonably well on any new platform that you took your code to. This is no longer true. And before this, even before this, there was this vector machines that people used for doing large-scale calculations. And again, that was a stable paradigm. And when people transitioned from vector machines to RISC machines, they had a stable time of roughly 20 years where their transitions persisted and were used. Also, that was earlier, those were the early days of science through computation, and so the codes were relatively simple and small. So it wasn't as daunting a task doing the transition of the code as it has become now in the current times when the machines are more heterogeneous. Within the machine there is heterogeneity, outside of course there is no end to heterogeneity, there is. So now we have a whole bunch of new challenges because there is, the machines are heterogeneous, but so are the solvers and the models, because as you understand more and more physics, you bring in more and more terms into your equation. Each one of them needs to be solved in a different way. So you have a mix of, you have that happening here also. And now, in the past, portability was similar to performance portability. Now this is no longer true, in the sense that you can take a code that is written in C and you can run it on GPU, but it's going to run absolutely crappily. So, I mean, you have to worry about those issues as well. And so what you can, so if you have a data structure layout that is good for one machine, it can be completely useless for another machine. So you have to worry about that as well. Codes are much longer, so the transition time is much longer than before. And platform cycle is much smaller than the code life cycle, very much smaller than code life cycle. Like I said, Flash has been in existence for 20 years. This was the time of ASCII read. And if you think about it, every 4 to 5 years, the machines change. So we've already gone through some 5 or 6 generations of supercomputers. And even when the machine model was relatively stable, these machines are at the bleeding edge, which means that their system software stack is also not very stable. So porting has never been a trivial issue. But now it has a completely different level of difficulty associated with it. It has gotten to a point where for a large number of codes, the platform life cycle is roughly the same as the life cycle it would take to transition the code to that platform. So by the time you're able to get your code ready to run on that platform, the platform is ready to die. And so you're never going to get any science done. So since there is no single machine model to target anymore, the only safety lies in deepening parallel hierarchy, including more abstractions in your code, and let the abstractions and middle layers do the heavy lifting for portability. So how can we approach that? And this is just one of the approaches. This is the approach that we are converging on in at least the partial differential equations domain and several of the other areas as well. The overarching theme is differentiate between the virtual view and the real view of the application, physical view and the virtual view. What this does is it simplifies the worldview at both ends and enables separation of concern. And then once you have these two views, you have to do some really hard-nosed trade-offs. And what do I mean by virtual view versus real view? So this is an example from the world of partial differential equations. You have a real view, you have a whole domain with many, many, many operators. And when I'm talking about operators, I'm talking about terms in your equation. So in the real view, what you do in order to parallelize and implement these equations is you have a spatial decomposition and you have a functional decomposition. Spatial decomposition is your domain decomposition, whether it is in the form of uniform grid or adaptive mesh refinement or any other way you can think of. Functional decomposition is that you have implemented different operators in different encapsulated units. So the virtual view is that functional decomposition leads to a collection of components, and the virtual view of spatial decomposition results in domain sections as standalone computation units. This was the old view that worked really well for distributed memory machines. And so the standalone virtual view of domain sections was used for doing what we used to in those days call the single PE optimization or memory access and compute optimization. And it also took care of parallelization and scaling optimization. And the collection of components basically fed into the virtual view of domain sections where each operator was operated on a separate virtual section. And so how much functional decomposition you did was basically the trade-off between flexibility and performance, because if you have far too many functions, so if you have too large a function, then it is unreadable. But if you have too many functions, then you have the overhead of function calls and your performance suffers. So that's the trade-off that one had to worry about is at what level do you break up things into smaller and smaller components. And then the enduring abstraction of partial differential equation solvers is this notion of ghost cells that let the component see a section of the domain as a complete domain. This is no longer sufficient. So now additionally what has to happen is now we also need abstraction at solver level, because now it is no longer true that you can take your, so in the past the operator was essentially implemented sequentially, and you ran the numerics as though it was running on just that process alone. That kind of hiding of parallelism is no longer possible because there is huge amount of parallelism within the node. And so you have to have abstraction at solver level as well. And so one has to rely on code transformation tools. So you express your calculation at a higher level, and you count on code transformation tools to generate optimized code, or not optimized, but the code that at least works well on many different target platforms. Similarly, the functional decomposition, now instead of looking at the trade-off here about flexibility versus portability, now you do is you definitely go into over decomposition, and again you're looking at abstraction tools that are able to fuse functions in order to increase the spatial and increase the data locality as the code is running. And similarly, there is dynamic scheduling, which then takes care of parallelization and scaling optimization. So now the memory access and compute optimizations are both done through some form of code transformation or the other. One is the translation of, say, a higher level function, a higher level statement into, say, a loop nest, and fusing functions by taking smaller functions and fusing them into a large function and turning it into a code which is in principle human readable but not really. So how do you go about doing it? You write solvers as independent tasks. You explicitly call out their dependencies and register those dependencies with the framework, and expose fusion possibilities, and then have a much more sophisticated framework that is able to hide all of these complexities. And I think I'm running short on time, so I'm going to skip over some of these things. I can answer questions about them later, but this is hierarchical decomposition through tiling and asynchronous execution, where all of these things, tiling, asynchronous execution, et cetera, are all handled by the framework, and they're hidden under the hood and not really exposed to the physics. So putting it all together, you express computation in form of stencil operators or other appropriate abstractions instead of explicitly written loop nests. You specify the part of the domain and conditions under which they apply, use masks to take care of branching, have mixed mode parallelism and parameterize the parallelism that you have. So instead of hard coding your loop bounds or your domain bounds, make them parameters that can be tuned for at compilation or runtime, have dynamic tasking, and so on. So that was all about the software architecture design. Now we move on to software process design. Again, when you start, because it has been emphasized over and over today that as important as software is, it's equally important to have a good process design, a good process in place if you want to have reliable results and if you want to believe your own results and be able to reproduce them. So again, the first step, like in architecture design, the software process design requires taking stock. Different needs for different projects. Blindly applying processes is always bad for productivity, because you should only pick something, because again, these things are overheads, and the way these overheads are justified is by reducing your technical debt. So you have to acquire overheads exactly so that you reduce your technical debt in as much as you need to. So smaller teams need fewer practices, whereas large team needs more, and the diverse teams need the most. Some process everyone should have irrespective of the size. For example, version control. Like I said earlier today, I even maintain all of my personal data on version control, because otherwise I can't keep track of my own life. Strong verification, it should just be into everybody's DNA, that you need to verify and verify and verify your code, because the consequences of making a mistake and not catching it early are always bad. And then documentation. I don't know about you, when I was roughly your age, I used to have this arrogance that I could remember every line of code I ever wrote. That was then. Now, and it was true also. Now I can't even remember. Now I can't even remember the directory in which I placed my source code, right? If I don't document it, I just completely lose track of where things are. So, and then map the team needs to process scope. So in small projects, you have the minimum set described earlier. If you have a software for internal use in a large team that is not doing any public release, you can have a simple software architecture. For it, it's always useful to have an architecture and coding standards and testing policies and documentation. Range of validity documentation needs to happen for everything. Even for your own codes, you should have a range of validity documentation. Contribution policies, as soon as you have more than one person contributing to the code, you should have all of these things in place. And then when you have large software with many interoperating moving parts, you need to have a software architecture that allows for separation of concerns, has well-defined APIs, has a well-defined infrastructure backbone. Software process should also consider things like release and license. And this I will talk about later in the next talk. And then it should have user support, maybe possibility for training users, because it always helps. Even training is not just useful for users, training is also actually useful for the developers of the project, because when you start to sit down to train somebody, you actually find very many shortcomings in your own design and your own software through the process. You want to have well-defined contribution policies for gatekeeping, intellectual IP, et cetera, and you have to have a way of resolution of IP and open source. So this is all about software design and so on. I'm going to switch gears again, and actually I'll take a question. No, I'll switch gears and I'll talk about community codes, and I'll go into questions later. So Flash is a community code. Flash is not the only community code. There are many community codes out there. There's NWChem, there's Amber, there is Cactus, there is Flash, and the Earth system modeling people have codes. The QCD community has community codes, etc. What's the motivation behind having community codes? Motivation is that scientists can focus on developing just their algorithmic needs, because in the community codes, a lot of the infrastructure, which is a very time-consuming part, comes for free. So instead of when you join as a graduate student, you have this problem that you want to solve. In the communities that have community codes, students don't have to start writing from day one, write a small subroutine, write the corresponding IO, and then make slow progress, and it takes 2 years, 3 years before you're able to do something that's really interesting. Where there is a community code, you take stock of what community codes are around, read a little bit of their documentation, find out what kinds of people are using them, see if it fits your need. You compare which one is customizable, you pick that code, you customize, and in 3 to 6 months, you're ready to already start producing scientific results. That's a hard to beat benefit of having a community code, right? So there is a caveat to this though. It is important to remember that even though you're using a code that was written by someone, if you start to use it without understanding the components that you're using of that code in terms of their range of validity, in terms of their limitation, then you can end up producing really bad results that have no scientific validity at all. So the principle, the rule of thumb in these situations is, if needed, you should be able to write the code. Not that you have to write the code, but if needed, you should be able to write the code. The other advantages are the researchers can build upon work of others and get further faster. because when you have a community code, typically the papers are published that tell you what went on in that code, and you have documentation, and so you can reuse some of the capabilities developed by others, and therefore, again, you can do less work and get more out of it. You get more reliable results because the code has been stress tested by many more people have seen it, and so with enough eyes looking at the code, more errors will be found. And they do, with open sources, you have more reproducible results. Other people can see the work you have done, and therefore your scientific results have greater validity and greater recognition. There are two models, Cathedral and the Bazaar model, that are sort of proposed by Eric Raymond. And the Cathedral model is that code is only available with each software release. The Bazaar model is that Bazaar model is effectively your open source model, where it is developed in view of everyone. Scientific codes mostly follow the Cathedral model, and there are many reasons for it. Some are valid ones, some are not so valid. Some of the valid reasons are that unless you have a very good gatekeeping mechanism in place, the quality of code can go down the tube very quickly in scientific software. Because it's not just the correctness, it's the convergence, it's the range of validity, it's all of those factors that come into play as well. And here the problem is that because the funding agencies have not bought into this need for gatekeeping and software quality wholeheartedly yet, it's very difficult to find funding for doing the kind of gatekeeping that you need to do. And so, and also typical user communities for scientific codes are too small to really support the Bazaar model, and the reward structure is incompatible. There are people who also give these, what I consider specious reasons that the code is too complex. That doesn't matter. Complexity of the code has nothing whatsoever to do with whether it should be a Bazaar or a Cathedral model. But even more misguided notion that keeps people from releasing their codes is that they think they have competitive advantage over over others in their field by owning that code. To me, that is intellectually bankrupt. And why is that intellectually bankrupt? Is that where your intellectual contribution is coming from new ideas, new ways in which you're going to be using that code, not from having some tool that no one else can use, and therefore you can continue to produce mediocre results because no one can even produce those mediocre results. So that's just my take on it. But the real reason is that the history of the development of the code and pride of ownership is what prevents people from going with the Bazaar model. The benefits of the Bazaar model are many in that, again, there are lots of beta testers, and a developer base, so bugs are found much more rapidly, and so the code becomes better much more rapidly. Debugging is parallelized. Infrastructure limitations are quickly exposed, et cetera, et cetera. Another one is that the capability addition is rapid. So in Flash, for example, the code started for astrophysics community, and people in compressible fluid dynamics, so an elliptical solver was added to do self-gravity for Flash. People came along who wanted to do incompressible Navier-Stokes solver using the pressure formulation, and the same solver was applicable to them. And then people in the incompressible fluid community found that the geometric multigrid they were using was not scaling, so they devised a hybrid algorithm that made it much more scalable, and people who were using gravity solver also benefited. So these kinds of synergies exist, and the capabilities multiply. So one community develops a capability, many communities get to use it. There is, there's a greater knowledge pool operating together, so there's more possibility of innovation because ideas are, the cross-fertilization of ideas is very much more there. But many of the reasons also go either ways, because if you have a bigger pool of, bigger knowledge pool means that there are more conflicting opinions, and therefore arriving at consensus can be challenging. And then prioritization can be challenging too. Gatekeeping can become a huge challenge, especially if there is no funding readily available for it. And where if orchestration of capability combination is higher if there is physics involved, because many times it just won't play well together. Scientific community codes follow several different paths. The most common path so far has been someone wrote a very useful piece of code that several people in the group started using, so then the code acquired a life of its own and collaborations happened. People moved, took the code with them, critical mass of users achieved, code became popular. Then it became too popular for its own good because no thought of extensibility and software design had been given to it. So people start trying to use the code and adding capabilities to it, got frustrated, a reset, the process cycle repeats, right? Huge amount of lost productivity in the process. So this is what, fortunately, finally, the agencies, the funding agencies are waking up to this huge loss of human potential and are doing something about this. But it is still very new and this is still in baby steps. A more sustained path is sometimes like-minded people, enough like-minded people will take it a step further. Some long-term planning will happen. They will sort of try to make sense and have a design in the code before it becomes too big, and then that code is more successful. This is the path that Flash took from version 1 up to its second version, where they wanted to use it for many purposes and therefore they invested some time in design and cleaned it up some. This model is still relatively rare, and in many cases it's even harder to make this happen. A desirable path is explicit funding to build a code for the target community with an implied support for design phase. The outcome is expected to be long-lasting and well-engineered. It is getting very hard to get this kind of resources. But when it works, outcome is capable and longer-lasting code. So there is a common thread about communities that flourish. Open source community codes and open source codes are found more often in communities where the threshold of minimum capabilities needed to get any meaningful result is high. So for example, if you are in a community where a single physics model is enough to get you results, you are unlikely to see a community code. Because, but where you need to have at least 4 or 5 different physics in order to get a sensible result, you will see that community codes will happen because people realize that you know, they can't roll their own. It's just not possible for 1 or 2 people to do it. The benefit of that is that sophistication in modeling advances much more rapidly in communities that adopt the community code mode, and it avoids the reinvention of wheel, et cetera, And I'll tell you that what we found, we did about the community codes. We did a survey of, so IDEAS project started 3 years ago, and we did a survey of use cases from the IDEAS project, which were the scientific codes. And so we looked at 5 application codes and 4 numerical libraries. We found that all of them had some minimum standards of software processes, and they were publicly available, but still the software process was relatively low key in those codes. And then this is the summary from Community Codes Workshop that was run at the University of Chicago in 2012, where the more longer lasting community codes participated, and their finding was that their software architecture was always in form of composable components. So they all had taken account of extensibility. They all had rigorous auditing process in place. They had gatekeeping for contribution, though models were different for different codes, and they all had wider user communities, and the communities were benefiting from having the community codes. There are some communities that are headed towards community codes, but the thing that runs across all of them is that they all have open source with governance structure in place. They have trust building exercises among teams. They have commitment to transparent communication, strong commitment to user support, interdisciplinary team or group of people comfortable with science and code development, attention to software engineering and documentation, and they understand the benefit of sharing as opposed to being secretive about their code. And with that, I'll take questions.